This video is about elementary row operations and the determinant. I presume that you've read through and worked through exploration 1, and you've gotten to theorem 2, where we show that if you form matrix B from matrix A by interchanging two different rows, it'll have a determinant that's the opposite in sign. If you obtain it by multiplying one of the rows by a non-zero constant k, it'll be k times the determinant. And if you add a multiple of one row of A to another, that doesn't change the determinant. Now, the proof of this theorem is tedious. We actually have a whole section, tedious proofs concerning determinants. But what I'd like to do is at least give you a sketch of the proof of theorem 2. That's the purpose of this video. So we'll jump to these tedious proofs concerning determinants and get underway. Let's scroll down to the section where we do the proof of results concerning the elementary row operations. And so what I'd like to focus on are the diagrams that we give you for each part of the proof. So imagine that this is matrix A and this is matrix B, where you can see we switch the two rows, row P with row P plus 1 basically. And imagine that the way we computed the determinant of A was to expand across the row P. Remember how you do that. When you're on a particular entry, like AP1, it's AP1 times the determinant of some other matrix. What would that other matrix be? Well, it would be you eliminate the row and column that P1 are in. Okay? And then you could do the same thing for AP2 times the determinant of some other matrix. And again, you eliminate the row and column that P2 are in, and you have some matrix. I guess I should say that this is plus or minus. It really depends on the checkerboard pattern and what row P really is. But then this one is minus or plus, because whatever that is, that one's the opposite, right? Because of the checkerboard pattern. Okay, so if we're going to talk about matrix B and finding the determinant and how they're related, let me change colors. So I'll change to blue, let's say. And let's go across row P again. Well, notice when you're at AP1, you eliminate exactly the same entries that you did when you found the determinant of A. And same when you're at AP2, you eliminate. So what I'm saying is, once again, it's AP1 times the determinant of, and I'm saying whatever this matrix is exactly the same as that. And AP2, whatever this determinant is, that matrix, the leftover piece is exactly the same. So whatever this is, this is. The difference is that switching the rows, because the checkerboard pattern, say it was minus plus in the first row, when you switch it, it becomes plus minus. And so you're changing every one of the coefficients. The AP1 that used to be plus or minus is now minus or plus. The AP2 that used to be minus or plus is now plus or minus. And so this gives you some indication of why, when we switch rows, the determinant of B will be the opposite of the determinant of A. Let's scroll down and look at the picture which talks about what happens when you multiply a row by a scalar k. So once again, I think the way to compare these two determinants is to imagine you're expanding along row P to compute. Once again, you'll see that it's exactly the same matrices being multiplied by the coefficients. AP1 times the determinant of some matrix, and then you have plus or minus AP2 times the determinant of some matrix. So I guess this time I'll go with red for matrix B. The only difference here is that in matrix B, because you have k's everywhere, it's KAP1 times the determinant and KAP2 times the determinant, right? So you can see very quickly, I think, that the determinant of B will be K times each of these things. And so if you factor out the K, it ends up being K times the determinant of A. Now the third property about adding a multiple of a row to another is maybe a little more challenging. So we're going to start off with this lemma. A lemma is a small theorem which you use to prove another theorem. And so that's what I'm doing here with lemma 4. Lemma 4 addresses the question, what if you have matrices A and B and you add them together to get matrix C? No, we're not adding the matrices. We're only adding one row of the matrices, right? So all these matrices have the same entries except for row P is different. In matrix C, row P is what you would get if you add the entries of row A, of matrix A in row P, and matrix B row P. And what should happen is the determinant of C equals the determinant of A plus the determinant of B. Let's see if I can sketch that proof for you. So again, let's expand along row P in each case. Because all the other entries are the same, you can see that to get the determinant of A, what's the first thing we do? We take plus or minus AP1 times some determinant, and then we do, I guess it'd be minus or plus AP2 times some determinant, right? Now what about matrix B? Well, I guess I'll do that in blue. So it's almost the same thing. These matrices are exactly the same. The only thing different is that we have BP1 and BP2 because we're in row P. Now what about matrix C? Well, that's the sum of these things. So if you think about it, it's AP1 plus BP1 times exactly the same determinant. So I think it's pretty clear that the determinant of C is going to be the determinant of A plus the determinant of B in this case. And so now we will use this lemma 4, to prove the theorem, the third part of the theorem, which says when you add a multiple of one row to another, you end up not changing the determinant. So here's the picture that will help us. Our target is this matrix B, because what we did was we start with matrix A and we add K times row P and add it to row Q. So I guess, K times row P and add it to row Q. And that becomes the new row Q, might be the way we said it earlier. So that's how we get matrix B from matrix A. But what we're going to do is we're going to show what happens by using lemma 4. And so we come up with another matrix A prime. It's the same as A, except that you'll notice the only difference is in row Q, where it used to say AQ1, AQ2, now it says KAP1, KAP2, right? So lemma 4 tells us that if you add these rows together, which is exactly what happens in row B, that the determinant of B must be the sum of those two determinants. Something about the determinant of A prime, because these two rows, one is a scalar multiple of the other, and so that says that this guy must have determinant of A prime must be 0, because these are linearly dependent rows. So we get the determinant of B equals the determinant of A plus 0. And so the determinant of B actually equals the determinant of A. I hope that you found this video worthwhile in understanding why Theorem 2 holds, even though we didn't want to write the entire proof in this section. You will get better at proofs by the end of this chapter if you work hard. When you do properties of the determinant, and even this section, there are certainly a number of proofs that you can handle that are not too tedious. The less enlightening ones we just put in section 5. Thank you.